Good morning, everyone. Let's get started. So in the previous class, we looked at a couple of tools which will be used to prove converse results in information theory. After discussing the Mrs. Gerber's lemma, we looked at the entropy power inequality, which said that the entropy power of the output of an additive noise channel is always greater than or equal to the sum of the entropy powers of the input and the entropy power of the noise. And this is an equality if and only if both x and z are Gaussian. And you can generalize this both for vectors and for the case where you have conditioning on some auxiliary random variable u. We did not discuss the proof, but then we saw one application which can be used to show that for any among all possible additive noise channels with a given power constraint, the channel which minimizes the capacity is the AWGN channel. So that is one reason why we look at the AWGN channel so extensively in information theory as well as digital communications. We also, I mean, when we're going through this, we also looked at maximizing entropy maximizing distributions, and in particular, we saw that among all probability density functions with a given mean and a given variance, the Gaussian maximizes the differential entropy. And we'll be using this frequently in many problems. So in particular, if you have, this also means that if you have an AWGN channel, then the capacity achieving distribution for the AWGN channel, the capacity achieving input distribution for the AWGN channel is also Gaussian. But one thing to perhaps note at this point is that all of this is under a first moment and a second moment constraint. Now, if we did not have maybe the second moment constraint, then the capacity achieving input distribution, even for the AWGN channel, would not be a Gaussian distribution. If let's say we had a first, second, and maybe a third moment constraint, or maybe only a first moment constraint, then the capacity achieving input distribution would not be Gaussian. So people study many of these constraints. So even for AWGN channels, people study the problem of achieving capacity and designing good codes under other constraints as well, not just the standard second moment constraint or the standard power constraint. For example, when you're dealing with problems such as communication over maybe visible light communication or communication over fiber optic channels, you don't have a second moment constraint. It's not a normal power constraint, but rather an intensity constraint. So, and this can be modeled by saying that the input should satisfy some L1 norm constraint instead of an L2 norm. And for that, the capacity achieving input distribution is going to be different. Okay, so these were the topics that we discussed in the previous class. In this class, we look at one more tool which will be used to prove converse results. It's called the Csisar sum. It's sometimes called the Csisar sum identity or the Kernel-Marton identity. And then we'll see some tools to discuss to prove achievability results. In particular, we'll revisit notions of typicality. So before we proceed, are there any questions from the previous class? Any questions?
Sir,
Yes.
sir, did we prove last time like the Gaussian distribution, the AWGN channel actually achieves minimum capacity?
Okay, I did not discuss all the steps of the proof, but
Okay.
but at least that roughly speaking, we did show that the Gaussian minimizes the capacity, right?
Okay, I'll check.
Sure. So it basically comes about from the fact that the entropy power inequality becomes an equality when the both the input and the noise are Gaussian.
Oh, yes, sir. I remember.
Right.
I remember.
Right.
Yeah, yeah.
Right. So, so this identity that we're going to prove now, it's called it's sometimes called the Csisar sum identity, but it's actually misattributed to Imre Csisar because he was not the one who discovered it. It was actually first discovered by Catalin Marton, and it was later used by Janos Kerner to prove some other results. So you'll recognize the names Csisar and Kerner because one of the textbooks, one of the reference books is written by these. So, but somehow, even though it was first discovered by Martin and it was first used to prove a converse result for broadcast channels by Janos Kerner, somehow, I mean, later on, Csisar had used the identity and that became popular, and therefore, at least the El Gamal and Kim textbook calls this the Csisar sum identity, but it should actually be called the Martin identity or the Kerner-Martin identity. So it basically says the following. It's a strange looking equality, and it basically just follows by a clever application of chain rule of mutual information. So it says the following. So if you have any collection of random variables u, xn, and yn, they could be arbitrarily jointly distributed, and there's absolutely no constraint. So it could be continuous, it could be discrete, doesn't matter. So as long as these mutual informations are well defined, the identity holds. So this basically says that the sum of the mutual informations of x between xi plus 1 and xn and yi given yi minus 1 u is equal to the sum of the mutual informations between yi minus 1 and xi given xi plus 1 through xn and u. Now, it's a little hard to give an interpretation for this identity, perhaps, but one way to perhaps see this is let's say you want to so if you look at this, then if you look at each of these mutual informations, then this mutual information is the mutual is so this is asking how much information does yi minus 1 give about xi given xi plus 1 through xn, right? And this is saying, or each term over here is basically represents the amount of information that yi contains about xi plus 1 through xn given yi minus 1 and whatever, an auxiliary random variable u. All right, so in some sense, what this quantity represents is, suppose you have a channel where you transmit xn and you receive yn. Think maybe a better way of interpreting, maybe one way of interpreting this is that, let us say that you have n transmitters and n receivers, and let us say that you're trying to estimate xi plus 1 or decode xi plus 1 through xn, or the messages for I plus 1 through n given yi, given that you already have access to yi minus 1, then this effectively represents the sum rate of this whatever multi-user problem. And the right hand side tells you something else. It gives the mutual information between xi and yi minus 1. So given y1 through yi minus 1 and already having decoded xi plus 1 through xn, then what is the maximum rate at which you can reliably recover xi given yi minus 1, right? So in some sense, you have, so the right hand side maybe is a little more intuitive. So you have y1, y2 up to yn. You look at one particular yi, and you have xi, x1, x2 up to xn. All right. So suppose that you already decoded these terms over here, xi plus 1 through xn. Okay, and you have access to all other yi's except all other yj's except yi. Okay, so having already decoded xi plus 1 through xn, you want to know how much, at what rate you can decode xi, right? But now you only have access to y1, y2 up to yi minus 1. All right, and this term over here basically represents the rate at which you can decode effectively. Right? So loosely speaking, this is the rate at which you can communicate such that xi can be decoded given y1 through yi minus 1, having already decoded xi plus 1 through xn. Okay, and the sum of these mutual informations in some sense gives the sum rate. All right, and it's saying that this quantity is equal to this particular mutual information over here. It's not a I agree, it's not a good interpretation perhaps, but we'll see an application of this when we go to broadcast channels. So many of the tools that we develop will be mainly used to study broadcast channels because in general the capacity of the general broadcast channel is still open. There are only very specific instances where we know what the exact capacity of the broadcast channel is. In general, we have upper and lower bounds on the achievable rates, but sometimes these can be loose. So people have devised a lot of different tools to study broadcast channels, and among them we have the Csisar sum identity, the entropy power inequality, Mrs. Gerber's lemma, and so on. All right. So let's see how to prove this. Yes.
So, sir, I have two questions. Like, first of all, just one clarification: is the summation is from I equal to 1 to n or equal to 0 to n minus 1? Because that in the mutual information it starts from xi plus 1. That means if I equal to 1, then it starts from actually x2 to xn. Like x1 is not included in both of the expression.
Yes, well, I agree. In some sense, this goes from I. It's still fine because even if you look at the right hand side, I goes from 2 to n.
Yeah. Yeah, so
Right.
my query is like xi is not appearing anywhere. So is it like x1 is not
So x1 is really not appearing anywhere. Yeah, right.
okay.
So both on the left hand side and the right hand side, x1 is basically not appearing anywhere. It's only x2 to xn which is being used, and I guess it's only y1 through yn minus 1 which is being used. Right? If you look at it carefully, if you look at the left hand side, this term, right? So if you look at when I equal to n, this is xn plus 1, which so this effectively is
Correct.
empty, and mutual information between this and yn, so that term is 0 in some sense. Right, so
Okay, sir. And another, yeah.
Go ahead.
Yeah, so another thing is like regarding the interpretation of these expressions, what you told in the right hand side expression, suppose we have decoded xi plus 1 to xn, Now we want to calculate how much mutual information it contains when with respect to the like I minus one instant of and xi.
Correct. Correct.
And so and in the left hand side, what it means actually, like I don't know whether I am wrong or not. So we have already decoded xi minus 1, and we got like we have received I minus 1 like random variable. Now we want to calculate how much mutual information it contains in the yi, in the next received symbol, and the
So you have to be a little careful because the conditioning is not on xi minus 1, it's on yi minus 1.
Yeah, that
Right?
is the
And
received.
that is different.
Yeah, that is the received received like the channel output at I minus 1 instant.
Yes.
So then it calculates what is the mutual information between the channel output at ith instance and the channel input at I plus 1 to nth instance, right?
Yes.
So what I'm saying is it like broadly speaking about like in which direction you are decoding, it doesn't matter, like the mutual information is same, because like the capacity you achieve is same, because here in the right hand side we are just decoding in the reverse direction. First we are decoding xn minus 1 and then till xi plus 1, right?
Correct. So in some sense, yeah, you're decoding in opposite directions, but uh, but yeah, I mean, both interpretations are not very good, I would say, because here again, so this really represents that you're decoding in one particular direction,
Yeah.
right? But this doesn't really represent that because you're conditioning on yi minus 1. So in some sense, this yi minus 1 is side information for not just the receiver but also the transmitter. So all of these interpretations just are not. I would say I don't have a good interpretation at this point. It is only when you apply that you will see how this is being used.
Okay, fine, okay.
All right. So it's maybe easier to interpret the right hand side. The left hand side is, yeah, it gets a little complicated.
Okay, sir. Fine.
All right. So to prove this, we'll start with the left hand side. So the left hand side is summation I going from 1 through n of the mutual information between xi plus 1 through xn and yi given yi minus 1 u. Okay. So I'll write this as, so I'll write each term over here. I'll split this using the chain rule of mutual information as follows. So the mutual information between xi plus 1 through xn and yi given yi minus 1 u is the sum overall j from going from I plus 1 through n of the mutual information between xj and yi given yi minus 1, xj plus 1 through xn and u. Okay, so I've done nothing here. I've just used the chain rule of mutual information for each term. The next step, which is kind of crucial, is that I'll interchange the order of summation. Okay, so here I'm first summing through I, and then summing through j. So first summing through I, which is the yi's, and then the j going from I plus 1 through n. Okay, this is the same as, so first summing from j. So j goes from 2 to n, and I goes from 1 to j minus 1. Okay, so the term inside remains the same, but I'm just interchanging the order of summation. Now what is each of these inner term going to be? I claim that this is equal to the mutual information between xj and j minus 1 given xj plus 1 through xn. Right? And this follows again just by the chain rule. Okay, so this identity basically just follows by two applications of the chain rule and an exchange of an interchange of the order of summation. All right. Any questions? Any questions? All right. So we've discussed a bunch of tools to prove converse results. Most of these yield what are called first order converses or weak converses, wherein we show that the probability of error. So if you try to operate outside the capacity region or if you try to operate at a rate above the capacity or above a certain rate, then the probability of error is always going to be bounded away from zero. So you can't make it, say, exponentially decaying to n. You can't even make it decay to zero as n tends to infinity. But in fact, it is possible to prove other stronger results as well. And in particular, in many problems, we're interested in proving strong converses, which say that if you try to operate at any rate or any rate tuple outside the capacity region, or if you're trying to operate at any rate above capacity or maybe some upper bound on the capacity, then the probability of error of decoding tends to 1 as n tends to infinity. And there are many different approaches to proving such strong converses, but maybe I'll just outline two of them. Again, I won't discuss them in detail because it's hard to discuss all of these in the course. But it's good to be aware that there are these tools and where to look for them if you're interested. So one sort of general class of tools is basically uses the following result called the blowing up lemma. So the blowing up lemma is used in a number of applications, both in computer science and physics and information theory. So it was first. So the blowing up lemma in a lot of generality was proved by Margulis, and it was proved and it was used to prove a strong converse by Alswede et al. And later a simpler proof of the blowing up lemma was given by Catalin Marton. And roughly speaking, it says the following. So if you have, or at least this is a version by Marton, it's not the fully general blowing up lemma, but generally the sort of result which is used in information theory. It says that if you have a sequence of independent random variables, not necessarily identically distributed, and you have a sequence of sets such that the probability that xn belongs to an is not decaying exponentially. Okay, so the probability that xn is in an is decaying. So if this probability is decaying at some rate, which is faster than any exponential, so it's greater than or equal to e to the minus n times epsilon n for some epsilon n which is tending to 0. So maybe it's decaying logarithmically in n, or maybe it's decaying even polynomially in n. Maybe it is 1 over n. Okay. Then if you slightly enlarge this set an, okay, so here gamma delta n of an is the set of all xn which lie within Hamming distance of delta n to a point in the set. So so you have the whole space, and then you have an, and the probability that xn is in an is larger than any exponentially decaying function. Okay, then if I look at a very small enlarging of this set, okay, that's what I call, so this is gamma delta n of an. So if you just enlarge it by a small amount, then the probability that xn is in this slightly enlarged set tends to 1 as n tends to infinity. Okay, that is what the blowing up lemma says. So this slightly enlarged set is called the blow up of an, and the blowing up lemma says that if the probability that that xn is in the set is not exponentially decaying, then the probability that it is in the blow up tends to 1 as n tends to infinity. And this is sort of in a form where you already see. So in some sense, the weak converse says that the probability of error is not decaying exponentially in n, whereas and basically this is used to prove this. This is used to prove the strong converse, which says that the probability of error is in fact tending to 1 as n tends to infinity. Okay, I won't show exactly how this is used, but in some sense, the strong converse makes use of the weak converse and the blowing up lemma to prove that the probability of error is tending to 1. So this is one tool which is used. The other tool, an even more powerful tool, which has been used a lot recently, is what is called reverse hypercontractivity, and it not just says that, and using this you can prove an even stronger result. So in particular, let us say that you want the probability of error to be at most epsilon. Okay, some quantity epsilon which is greater than 0. So for a fixed probability of error, then so for this fixed probability of error, what is the maximum rate that you can at which you can transmit? Right. So that is what is called a second order. That gives a second order result. So you want to know how large can kn be. So you don't just want to know what kn by n tends to. You want to know exactly what kn is. And it's possible to show that kn, the largest kn that you can have for a given probability of error epsilon, basically grows as n times the mutual information between x and y, or n times the capacity, plus square root of n times some function, plus some third order term which decays faster than root n. All right. So this is what is called a second order result. So if you try to operate at any rate, or if you try to transmit more than these many bits across the channel, then the probability of error will be strictly greater than epsilon. So this gives a very tight bound, not just on the rate, but on the exact number of bits that you can transmit for any n and any finite probability of error. Okay, and once again the reverse, it's a little more. The reverse hypercontractivity statement is a little more complicated. It says that if you have any, if you look at any function, so two random variables x and y are p, q, reverse hypercontractive, if for every functions x and y, the expectation of f of x the expectation of f of x g of y is greater than or equal to expectation of f of x raised to the p whole raised to 1 by p times expectation g of y raised to q whole raised to 1 over q. It's a complicated looking statement, but what this effectively implies and what is used a large number of times is that the probability that if you take f and g to be indicator functions, then the probability that x is in A and y is in some B is greater than or equal to the probability that x is in A whole raised to 1 over P times the probability that y is in B raised to 1 over Q. So the joint distribution in some sense is dependent only on the marginals. All right. So these are two tools. Again, we won't discuss these in detail, but it's good to be aware that there are these tools. Right. So this wraps up our discussion on converse on tools to prove converses, and now we'll go to some achievability results. Right, so this will be just a recap of what you've already seen in the information theories course as well as the source coding and channel coding course, and we'll see some more newer results starting from next class onwards. Okay, but before that, any questions? All right. So let's start with let's recall the definition of a typical set. After all, most achievability results in information theory are proved using the notion of typicality. You start with a typical set encoder. You start with you do typical set decoding, both for source and for fixed length source and channel coding. Right. So we define the typical set. There are different notions of typicality, and this notion that we will use, this is what is used in the book by El Gamal and Kim. It's sometimes called robust typicality, and it's a stronger version of typicality than what is there in the Cover and Thomas textbook. Right. So let's look at the following quantity. I use slightly different notation from the El Gamal and Kim textbook, primarily because they use x and y instead of px and py. So the typical set is really a function of the distribution and not the random variable itself. Right? But anyways, so given any sequence xn and any symbol a, I'll denote mu a of xn as the fraction of occurrences of the symbol a in xn. So if I have, say, 1, 3, 2, 1, 1, 1, 3, then let me call this x. Then what is mu1 of x equal to? It is 1, 2, 3, 4 divided by 7. Mu2 of x, the fraction of occurrences of the number 2 in this particular sequence is 1 over 7, and mu3 of x is 2/7, right? So this is what I call the type of the sequence. It's basically the empirical frequency of the sequence, right? The empirical frequency of symbols in this particular sequence. Okay, so that is what I define as mu a of xn. So a sequence is said to be typical if the fraction of occurrences or if the type is close to the true distribution. So if mu a of xn is minus px of a, if this is close to, if it is less than or equal to epsilon times px of a for all symbols a, then we say that the sequence is typical, and the set of all typical sequences is called the typical set, which will denote p epsilon n of px. All right, and for the typical set, we're interested in the following questions. So, what is the probability that a random sequence drawn IID according to px is typical? Yes.
So, is it commonly known as strongly typical set? Like
it's actually called robust typical set. It's actually not the strong typical set. The strong typicality typically usually says that this quantity is less than or equal to epsilon by size of x. So depending on how what you have. So if you have this instead, then this is called strong typical. So this notion is called generally robust typicality. Again, different papers have different names for these things, so it's not, you don't really have to associate something to this, whatever we can call it, Elgamal-Kim typicality. But I think the robust typicality was originally used by I think Orlitsky and others, and it's useful. We'll see that this has a very useful form and it gives some nice results. Okay, so
yes.
so even though this notion of typicality is very useful in proving a lot of results for MAC and broadcast channels. So if you look at Cover and Thomas, then the definition of the typical set is slightly different. So let me call it weak n of px. So this is the Cover-Thomas definition of typicality. So it is a set of all sequences such that log 1 over p of xn is minus the entropy. So this is less than or equal to epsilon. Right? So some such definition. Right? So these are two different notions. You can it's easy to show that if a sequence is epsilon whatever robust typical, then it is some epsilon prime weakly typical, whatever Cover-Thomas typical, but the reverse is not necessary, is not true. So just because a sequence belongs to this set, it does not belong to this. It may not belong to this set for any epsilon prime. Okay. And but nevertheless, this definition of typicality is although it is not useful for multi-user information theory or the kind of problems that we will study in this course, it is still very powerful and very useful because in particular when you study random processes and particularly sequences or systems with memory. So in those notions, instead of using log 1 over, so this h of x will be replaced by the entropy rate, and basically it says that that it's a set of all sequences whose for which the log 1 over the probability is close to the entropy rate. And when you're trying to prove, say, source coding or channel coding results for systems with memory, this notion of typicality is more useful, because of course this notion doesn't really make sense. But both of these can be generalized. Okay, so that was sort of a diversion, but broadly speaking, the following, we'll be interested in the following properties of the typical set. We'll show that the probability that the sequence is not typical tends to 0 as n tends to infinity. In fact, it decays exponentially in n. So the probability the sequence is not typical decays exponentially in n. And what is the size of the typical set? The size of the typical set is roughly 2 raised to n times h of x, 2 raised to n times the entropy. And for any sequence in the typical set, the probability of that particular sequence we'll see is roughly close to 2 to the minus n raised to h of x. Okay, and because of this particular definition of typicality, we can prove the following very interesting result, which is also very useful. It says that if you look at, take any, so suppose you have some xn which is epsilon typical. So I'll say that the sequence is epsilon typical. So xn is epsilon typical if xn belongs to t epsilon of px. Okay, so if a sequence is epsilon typical and you have any non-negative function from this set to the set of the real, so any non-negative function g, then and you take and you average g over xi. So you look at 1 over n summation I going from 1 through n of g of xi, then this quantity is very close to the expectation of g of x taken with respect to px. Okay, so in some sense, the average of g of x, the empirical average of g of x, is always going to be close to the true average if xn is typical. Okay, and let's see how to prove this. So I claim that this quantity over here is equal to 1 over n summation. I'll rewrite this in the following way. I'll sum over all a in x, and I'll sum over all I going from 1 through n g of xi times the indicator function, that xi equal to a. Okay, so I'll just group together all xi's which are equal to some particular a. Okay, and just count the contribution of this sum towards some particular a. Okay, but this is equal to 1 over n summation a in x g of a. So note that in this term, we're only counting those xi's for which xi equal to a, all those i's for which xi equal to a, and obviously xi is always equal to a. So g of xi equal to g of a. Right. So this is g of a times summation I going from 1 through n, indicator of xi equal to a. Right, but what is this term equal to?
mu a.
Correct. So it's actually not mu of a, it's n times mu of a.
N times a.
So it's 1 over n summation a belongs to x g of a n times mu a of xn. So the n and n cancels. But you know that mu a of xn is within an epsilon of px. Right? So this is less than or equal to summation overall a in x g of a times 1 plus epsilon px of a, and it's greater than or equal to g of a times 1 minus epsilon px of a. Because by definition, so mu a of x minus px of a, the absolute value is less than or equal to epsilon times px of a. So mu a of xn for any typical sequence xn is within 1 plus or minus epsilon times px of a. Right? And basically, and that is exactly what I'm using over here. So if I take the 1 minus epsilon and 1 plus epsilon outside, I just get expectation of g of x. So this empirical estimate or whatever, the frequency of occurrence of g of xi is going to be bounded between 1 plus or minus epsilon of the expectation of g of x. Okay. Any questions?
Sir?
Yes.
So, like typically, how like g looks like g is a function, right? That takes a
G is
value
any
from.
function. It doesn't matter what function it is. It just has to be a non-negative function of the reals.
Okay.
So for every function, the statement holds.
So it takes value from the alphabet and then it maps to a real number.
Yes.
Okay. So can you give just one example? Like it can be any function, any non-negative function, like.
It can be any non-negative function. So maybe okay. So let's take the okay. So one example is let us say that x is, let's say, the output of the binary erasure channel. So it can take values 1, 0, and erasure. Right? And maybe the function g goes from 0 to plus. So maybe I want to count the fraction of erasures. Okay, it's one particular example, right? And this counts the fraction of erasures. So my g of 1 equal to g of 0 equal to 0, whereas g of e is equal to 1. Okay. So if a sequence of uh, if a particular sequence is typical, then this basically says that summation I going from 1 through n g of xi, or the fraction of erasures, is going to be close to the expected number of erasures. So that's one thing, right? So it's 1 plus epsilon times expectation g of x. So let's see, maybe take some other example. Say that you are transmitting something, maybe using QAM, okay, or maybe even QPSK. Maybe this is the, or let's say whatever, 128 QAM. Okay. So this is my alphabet. So I'm going to transmit n symbols, each symbol which comes from 128 quam, let us say. Okay, and you give some particular input distribution on 128 quam. This is the distribution that you choose, and this distribution is chosen so that maybe the expected power, so the expectation of x square is less than or equal to some particular quantity p. Okay, so in this case, g of x is equal to x square. Okay, then so if a sequence xn is typical, then for any typical sequence, summation I going from 1 through n, x square is going to be less than or equal to 1 plus epsilon times the expected power, which is 1 plus epsilon times p. If a sequence is typical, then it says more. So as long as the sequence is typical, then for every function this happens. So the expectation of x is going to be less than or equal to 1 plus epsilon expectation of x, 1 over n summation over I xi cube is going to be less than or equal to 1 plus epsilon times expectation of x cube, and so on. So it doesn't matter what function you take, right? You can take x square, x cube, x to the 4, whatever, and even then this statement will hold, right? So the empirical average of g of x is going to be arbitrarily close to the expectation of g of x.
Got it, sir.
Okay, so let's look at this. So we want to at least let's quickly try to derive some properties of the typical set. And so the first thing what we want to know is what is the probability that a random sequence is not typical. Px, right? So the way to analyze this quantity is to look at the random variable mu a of xn. So take a random sequence xn. So a sequence is not typical if mu a of xn minus px of a is greater than epsilon times px of a for some a. Okay, so this is the probability that the sequence is not typical. Now mu a of xn, as we've seen, is the fraction of occurrences of a in xn. So this can be written as summation I going from 1 through n, the indicator function of xi divided by n. Right, so this is the trick that we'll use to analyze typical sets and typical sequences. So mu a of xn, the fraction of occurrences of a, is the sum over all I going from 1 through n of this indicator function, which is equal to 1 if xi equal to a and 0 if xi is not equal to a. So this is 1 if xi equal to a, and 0 if xi is not equal to a. Right? The advantage of looking at this is that this is a sum. This is a sum of IID random variables, right? Since each xi is IID, this random variable, which takes value 1 when xi equal to a and 0 when xi is not equal to a, this is a sequence of IID random variables. And what is the expectation of mu a of xn? So what is this equal to? Or
1 upon
what
n.
is, sorry, yes?
1 upon n.
1 upon n times what more? There's something more. So is 1 upon n I going from 1 through n of expectation of the indicator function, right? But what is this expectation equal to? Right? So what is the expectation of this indicator random variable?
1, sir.
It's not equal to 1, right? So the indicator function is 1 only if xi equal to a, and it's equal to 0 if xi is not equal to a. Belongs to x of px of x, indicator x equal to a. So this is the expectation, right? So if we just plug in the formula for expectation, expected value of this random variable, then it gives you this. But what is this quantity equal to? Yes? So what is this expectation equal to?
Kind of number of times x is equal to a into px of x.
So this function takes, it's equal to 1 if x equal to a and 0 if x is not equal to a, right? We're summing over all possible x. So what will this give you?
Acha.
Right? So take an example. So let's say that x can take values, whatever, alpha, beta, gamma, delta. Okay, so this is my x. Let's say that the occurrence probability is 0.1, 0.2, 0.3, 0.4, right? So this sums to 1. And I want to know what is the expectation of the random variable indicator x equal to maybe beta, right? So this is summation overall x, so x equal to alpha, beta, gamma, delta, the probability of that particular symbol times the indicator function of x equal to whatever beta. Right? So what will this be equal to?
The probability of occurring beta.
Correct. So it's just
0.2.
0.2, which is the probability of occurrence of beta, right? So in general, what is expectation of indicator function of x equal to a?
One, like the sum of all.
No, x equal, so for a particular symbol a.
Oh, sorry.
Right?
Okay.
So that's what I want here.
It's the
Right?
probability of occurring A.
Okay, so probability of occurrence of a, right? So it's just px of a. So the expectation of mu a of xn is simply px of a. Right? So this is equal to in expectation, right? So it's a sum of random variables, and the expectation is px of a. All right. So what can you say about this particular probability? I claim that this probability tends to 0 as n tends to infinity. Why?
So can you just repeat this last statement, sir?
So what do we want? We want to know what is mu a of xn minus px of a greater than epsilon px of a, which is basically the same as saying 1 over n summation I going from 1 through n of this indicator function xi equal to a. This is a sum of IID random variables, right? And the expectation of each of these is equal to px of a, as we've just seen. I claim that this probability tends to 0 as n tends to infinity. Why?
Sir, 1 by n summation indicator function x equal to a, it approaches to p of xa when n tends to infinity.
But in what sense does it approach px of a? So this is a sequence of random variables,
Yes.
right?
Yes.
So have you seen this statement in a previous class?
In some bound. Okay.
Yes. I mean, okay, so you can use a specific bound, but there's a more general result. I'm not asking for an explicit upper bound for each n. Okay, so for the next class, you should revise those topics, the basic topics in probability, because those are very important. We will be using them extensively in the next few classes.
So by using Chebyshev inequality, we can prove this.
Sure, you can use, of course, you can use do it using Chebyshev's inequality, but you've seen this very specific statement. What is it called?
So it converges almost with it converges with probability.
Correct. So it's convergence in probability, but what result have you already seen which says this?
Almost sure convergence, sir.
No, we don't want almost sure convergence here, right? It's convergence in probability. This is just the weak law of large numbers, right?
Yes.
So this is just the weak law of large numbers.
Yes. Yes.
Right? Okay, so that's why you should go through the basics once again. So we will be extensively using the Chernoff bound, the Chebyshev inequality, and the weak law of large numbers. So you should go through that before the next class. All right. So any questions? All right then. So we meet next week in the next class. So go through the basics, and we'll go ahead with properties of typical sets. We'll see joint typicality and conditional typicality and various notions, and then we'll apply these to and try to derive some achievability results, both for the point-to-point channel coding theorem and also some source coding problems.